My name is Timothy. I'm a postdoc and I work under the supervision of Daniel Williamson. Most of my PhD was about optimization, and so here I'm also trying to do a different kind of optimization in order to help for decision support. So, quick reminder of what the tool looks like, and I'll introduce what I'm working on. So this is the first page where basically we try to find the best strategy that matches the targets set by the sliders on the right-hand side. So I have been working for the last year mainly on trying to find the best solution for this, the best planting strategy that matches the constraints that we have on the right-hand side. Tab 2, we try to find 4 strategies. Now, currently, they're all random, and part of my work is also involves trying to find pretty different strategies for this that's feasible, different strategies. Tab 3 is about eliciting preferences from the user. I am not working on this at all currently. That is for a bit later. So Bertrand yesterday introduced a way of getting the optimal solution for tab 1. I'm doing something slightly different and turn this into an optimization problem. So I wasn't sure if everyone is familiar with optimization in general, so very quick introduction to it. Then I'll introduce the Bayesian optimization that I'm working on, introduce some related concepts that I've had to work with, and well, the actual results that I can get from this. Lastly, I will talk about what is left for me to do to make the whole process better. So what I'm doing is mainly about optimization. So the idea is, given a random data set or a function, you want to find the minimum or the maximum. I'm focusing on the minimum. So the classical way is with something called frequentist optimization methods. And typically they look at first and second order derivatives in order to find the most likely best next point that might be the minimum. Now, the problem with those is that the function that we have might be really costly to evaluate. So if we're dealing with Joules simulators, we can't afford to run it on a lot of data points. And more than that, the function that we want to optimize might be a complete black box. Bayesian optimization can work around these two problems. So the function I'm working with, I'm reusing the notation that Danny introduced yesterday. So the idea is we have a planting strategy, P, on the left-hand side, and the objective function that I'm trying to minimize is a combination of outcomes. So given that capital P is a planting strategy, small p would denote the user preferences. So currently I'm not dealing with this, and they're all 1. This denotes the outcomes that we want to optimize on. So for example, the ones that we want to minimize would be the total area. So we want a strategy that doesn't involve planting in every single cell. We want to minimize the total area we plant on for, well, financial purposes. And the outcomes to maximize would be, for example, the carbon that we want the planting strategy to store in the ground from the air. Now, so given that the point is to minimize the objective function, if I want to find a strategy that minimizes the area, I have to put them as a positive, and the ones that I want to maximize, like carbon, I have to put them as a negative outcome. So the idea is that if I want to minimize this entire thing, those two numbers will will try to find the strategy and go in opposite directions. So here, we want to minimize the total area while maximizing the carbon. Each one ensures that we find the strategy in different directions. These terms are art inner art because we want to find, for example, an area that has a maximum amount. So we don't want to go above a certain threshold. Those are the sliders that we had on the right-hand side in the previous pictures. So we set a ceiling at a total area sum, and we want to avoid going above that ceiling. Similarly for carbon, we want to avoid going below a certain level of carbon stored. So these ensure that if we go beyond those limits, the value of the objective goes really high. So given that the point is to minimize it, this ensures that the constraints are respected. Now for tab 2, we can take the same objective function, but remove the outcomes that we want to maximize or minimize. So for tab 2, we want to explore different strategies. So we don't need to maximize the carbon stored or to minimize the total area. We only care about finding all the feasible solutions. So this is a bit trickier because basically this is a function that has a 0 over all feasible strategies and positive values outside of that. So we do not want to find the strict minimum because we already know it in advance, it's 0. We want to find the space of all the zeros. So given that P, currently I'm working on a simplified problem, which is that the strategies are defined simply by a binary vector of planting or not non-planting per parcel. So it's the Falmouth example I will show later has around 350 dimensions. This is an issue, mainly because in Bayesian optimization, we need to train a surrogate model, a GP, and 300 dimensions is way too large. So in order to generate random data to feed in the GP and find the optimum, we need a way to generate both high dimensional data in 300 dimensions and low dimensional data that corresponds to it and that we can train the GP on. So the idea of random embeddings is a way to generate both low and high dimensional data at the same time. So on the left-hand side, in Y, we have an example of a low dimensional variable. Here b equals 1, but in practice we take 5 or something like that. And then the idea is to create a random matrix A, as a Gaussian random matrix A, normalize it, and project the data, the low dimensional data, to a higher dimensional space, the embedding space. So the idea would be we generate a random real vector in the low dimensional and then multiply it by a random matrix to augment the dimension. Now, the paper that introduced this, the idea is that in the high dimension, a lot of those are not important. And importance is mostly in the sense of the variables are, or some of them are highly correlated with the others. So in 2-dimension, this is what the idea looks like. X1 here is the important dimension because the objective varies a lot according to it. X2 is the less important dimension because the values are fairly constant with respect to X2. So the idea is we want to go through the high dimensional space from a low dimensional one. So, and the way to do it is to go through only the important dimensions. So here, for example, we would not really look at making X2 vary, but we would vary mostly X1, and that would allow us to traverse the space of important dimensions mainly, and keeping the others fairly constant. So this is, so given a certain, so the original paper looks at box constraints. For this, in the high dimensional space, I do not deal with those because my variables are categorical. But so the idea is here we have one important dimension and not the other. So we go through the embedding space in we try to go through most of the box and avoid varying too much in the unimportant dimensions. So what this allows us is in one go to generate both low and high dimensional values that correspond to each other and can somewhat be transformed back and forth. Not exactly, but almost. Now, the Bayesian optimization works in a similar way to frequentist optimization. The main difference is that instead of looking at the objective function every time, we emulate it with a GP and then look at the GP outputs in order to find the next best point to actually look at and see if we have a minimum. So how it works is we start with a random data set that we generate from scratch. We pass it to the objective function and then emulate a GP on those outputs. So the idea is the GP would be trained on the low dimensional inputs and the height and the outcome from the objective function. Then we look at a new random set of points. We try to maximize something called an acquisition function that will help us figure out which points are most likely to minimize the objective. So we select the ones that might be interesting given the GP, and then evaluate the objective on them. This gives us iteratively next best set of points, and we can iteratively find the most likely next lowest value for the objective. Once we do that enough, for tab 1, the idea would be to look at the only minimum of the object of all the outputs that we generate this way. And for tab 2, we would look at all the zeros that have been, the arguments for all the zeros that have been generated. Now, the acquisition function has not been talked about yet, so a brief introduction to the one I'm using. If we define the improvement as the either 0 or the reduction in minimum from the new point we're looking at, the idea is that we can say that we can approximate it with a Gaussian. And from there, we can then look at the expected value, integrate that, and some calculus gives us a nice formula in the end. Now, this has a few modifications that are doable. For tab 1, this is fine, but for tab 2, I know that the minimum is 0, and that this acquisition function would try to go below 0, and if a point is already at 0, I do not want to. It is not possible to go below. So there are some ways to deal with that, such as introducing a constant reduction in the left-hand side. There is another paper I have in a future slide that talks about a way to adapt this in the case that we know when the objective is at its lowest point. In practice, this is what it can look like given a random GP in one-dimensional GP. So if we have it, so here I selected a random set of points in green as the true function output, trained the GP on it. In the blue are the estimated means of the GP, and in red are the error, the margins of error for each of the points. So the error is 0 at each true output, and outside of those, it forms bubbles because we're not sure what the true output is at those points. So the idea is the acquisition function will find the most find the most likely minimum. And here we can see that it's very likely to be between 0 and 0.25. So we would look at that maximum, we try to find that maximum, then update the GP and our collection of outputs. Now, because this in practice is only adds one point at a time, I'm and because I'm also dealing with multiple dimensions, and I've still trying to do a multi-start optimization of it, because the idea is we might have a lot of local maxima, and I wouldn't know when I find the global maximum. So if I try to optimize it a lot of times, given different initial values, this might be slightly better. This lets me look at likely points that might be the minimums, but more than just one at a time. Given that each iteration of Bayesian optimization takes a while, this should help a lot. So this is a paper that was published a few years ago when that I need to look at a bit deeper. The idea is, I explained it earlier, when we know that for tab 2, the optimum of the function is known, we don't need to try and go below it because it's not possible. Brief introduction to GP kernels, because it took me a while to play around with them. The idea is we need to define a covariance structure. I tried a few different ones for the GPs. Currently, the Matern one seems to perform the best. The diffusion one, I tried it when I had a load back when I was dealing with decision units and not individual parcels. The dimension was low enough that my inputs were categorical, so I tried diffusion kernels. In the end, the Matern one is the fastest and is pretty good at what it does. For later on, Danny has recommended me to use a custom kernel that he wrote about some time ago. And given that I'm dealing with quite a few dimensions, currently I'm only looking at the planting strategy is only defined by the areas. I'm dealing with a simplified problem. As Danny mentioned yesterday, I will have to introduce, for example, the year of planting as a parameter and the species of I want to plant as a parameter. So I will have to deal with, I will most likely have to try and combine different kernels that in order to deal with those different variables. So this additive kernels is one way that was introduced by Devono in 2011 to combine different kernels, and also importantly to approximate them, because calculating covariance matrices takes a lot of time, and approximating kernels with this makes that calculation pretty much faster. So when I try to maximize my objective for tab 1, this is one way to visualize the results that I get. So the line is pretty understandable. So here I only plot the total area, the total sum of parcel area versus the sum of carbon stored by the different planting strategies. And each dot represents a different planting strategy that I have looked at, that the optimization process has looked at. So the line here, the trend is pretty normal, because if we add more parcels, we increase the total area planted and the carbon stored at the same time. If we plant more trees, basically it takes more space but stores more carbon. So the lines in red are the thresholds that I have done that I showed on the first slide. So the idea is we simulate a lot of these, and we're only interested in the upper left quadrant because we want the area to be below a certain value, and we want carbon to be above a certain value. So we're only looking at this space here. When we zoom in it has a few solutions. I think in this one it was around 20. So the process works, and now among those 20, then there is the preferences of the user to take into account to figure out which one would be best in that cloud. Currently, I do not do any rescaling or use any special preferences. So carbon, because it has a high value, is favored. So currently the best solution would be this one because it maximizes the carbon. So for example, for the first tab I showed, this is the results for the Falmouth area that I get. And in order to have an area at maximum, to have an area of 3.5828 and a carbon stored of 62, this is the result that we get. It looks at roughly 40,000 different strategies in about 1 minute. So it is pretty good. A few weeks ago, it was about 15 minutes. It still can help. It still can be accelerated a little bit. The EU introduced, and Bayesian introduced the Vecchia approximation. I'm using that already, but it's still on the order of a minute, which is not really ideal. Tab 2 has fairly similar results. It also explores the space of feasible strategies, but this time we're not interested in the maximum, but all the points in that upper left quadrant. There is no maximum, there is no best solution anymore, because we're trying to find all the ones and find a way to have 4 very different strategies in some sense. Currently, I'm not I'm not handling what it means to be very different. That will come later on. So here is an aggregate of the results for the tab 2. So I plotted all the strategies, and in blue, the blue dots, the blue parcels means that the parcel was not present in a lot of strategies, and red means they were present in almost all of the strategies. It's not only red or blue, it's combinations. So some are purple, and there are 16 different colors in this. It's a bit hard to see, but anyway. So so far it works pretty well, but there are a few avenues for making it run a lot better and find better estimates. So far I looked mainly into simple ways to do multi-objective optimization, because I have a sum of different objectives that I want to look at, and I did not really touch on that. I also implemented a very basic penalty. There are lots of others that are doable. I need to also look into all of this. Next, there are also slightly different problems, mainly related currently to the biodiversity results that I have not implemented at all. And the main thing I'm working on right now that takes most of the time for the optimization is maximizing the acquisition function. That part takes a while. I'm trying to figure out with the U if there is a way to do it in parallel so that it would take much less time. Yeah, there are quite a few things to do for later on, and that's about it.